Alright, what we got going on, we're continuing these notes. We're naming complex, actually coordination compounds that involve complex ions. Alright. So, it gets kind of fun here. We have a molecular formula, and we got to write the name. En, that's a new one. En, what is En? That's ethylene diamine. Ethylene diamine. So we'll write that over here. En equals ethylene diamine. Ethylene diamine. Just want to make sure I'm doing it right. Got my waterlogged note sheet. It's intact still, so alright. So the first things first, we've got the complex ion, and then just the anion right there. So we can name that I'm going to put it right here because it's probably going to be a long name. They've been kind of long. So we're going to write sulfate, and we got to name the complex ion. First things first, you got to name the ligands, and then you got to do it in alphabetical order. We got ethylene diamine, and we've got nitrite, NO2, and let's see. Which one comes first, E or N? I think it's E. Yeah, E comes first. So we were just, I heard in the background because all my kids are doing virtual learning too, and there's this kind of fun little alphabet song, and E definitely comes before N. So we're going to do ethylene. Diamine. And that's what En is. Diamine. Diamine. That's an N. And then we got to do dinitro. Why? Because, well, taking a step back. NO2 is nitrite. And whenever you have a negatively charged ligand, and that's definitely, it's a negative 1 charge, you got to add O to the ending, so nitro. But there's 2 of them, so we're going to call it dinitro. And you guys probably, some people probably already have this done. So feel free to kind of do it on your own as I walk through it. We got ethylene diamine dinitro. All right. So you should probably put di in front of this because we got 2 ethylene diamines, so it'd be like diethylene, diamine, dinitro. But the thing is, before you write di, they like to make it more confusing. Because ethylene diamine already has di in it, they make you use the word bis. So it's actually a bis ethylene diamine, to show that you got 2 of them. Otherwise, it looks like you have ethylene, just like 2 of them, and then 2 amines, and they're 2 separate things, and that would confuse someone who really knows complex ions. Yeah, and I'm not going to have anything like that on the test, but just know if you do have di already in the name of the ligand, and you have 2 of those things, then you got to write bis as 2. So this is kind of confusing. So there we go, bis ethylene, diamine, dinitro. We just got to figure out the transition metal is iron. It's not the negative anion, so we're not going to call it ferrite. We're just going to call it regular iron. So I don't call it iron because it's the cation. Then we got to figure out the charge, and that's going to be the Roman numeral. Ethylene, diamine, neutral charge, not going to impact it. Nitrite, -1. Sulfate's -2. So we do the mathematics here. 0 equals X for iron, -2 for the 2 nitrites. Ooh, it gets complicated here because we have 2 complex ions. So, okay, so sulfate is -2. Therefore, the complex ions together must equal +2. But I've got 2 of them. So that means one complex ion would be a +1 charge. So we got +1 equals X -2 essentially. I'm going to add 2 to both sides. And X is going to equal, in this case, 3. Questions on how I got that? Got to really kind of think mathematically. Okay. Alright, so why don't we try, how many more examples of these do we got? Yeah, just 2 more. This is the flip side where we got to write the formula. So why don't we try this one together, and then you guys can try the last one on your own, and then we'll go over it. Or do you guys want to try both of them on your own? Okay, we'll just go with what I said then. Alright, so triamine bromoplatinum 2 chloride. So I know at the end is chlorine, alright? And then my complex ion, let me just do a rough draft over here just in case I make a mistake. We got 3 amines, that's NH3 is an amine, and there's 3 of them. They're neutral. Bromo, Br, there's just 1 of them, and that's -1. And then platinum, so typically you write the transition metal first. So we got platinum, and chloride is -1, so we need this complex ion to be a +1 to offset that. Alright, so how do we get it to be +1? +1 equals X -1, because you got unknown, neutral, and then -1. I'm going to add 1 to both sides. That means my X is going to be +2. That's the charge of platinum. I'm going to plop this right here. That was my rough draft. Looks like I did it right the first time. NH3, 3 bromo. Oh, they told me the charge of platinum. What am I doing? I didn't even have to do any of that math. It's +2. That's what it is. Okay. So, but if you want to be sure, there it is. I think that's it. Yeah. I'm going to put this in brackets so that we know that that is the complex ion. If it's not in brackets, then it looks a little... Yeah, you'd need to have it in brackets because you're not sure if this bromine and chlorine... Well, you could figure it out, but it just looks cleaner if it's in brackets. Questions on that one? Alright, so I'm going to let you guys try potassium hexafluoride cobaltate 3 out, and then we'll go over that one. I'm going to pause the video so people don't... Alright, we're going to chug through this one just because we only got 35 minutes and then we're done already. Potassium hexafluoride cobaltate. Alright, so I know potassium is K for sure. That's not a part of my complex ion, so my complex ion is hexafluoride cobaltate 3, negatively charged, which is why we got 8 for the transition metal. I'm going to do a rough draft so I can make a clean answer. Cobalt is listed first, and then we got hexafluoride. That's 6 fluorines. Oh, that's simple. Alright, so we just got to figure out how many of these we need. I know cobalt's a 3+ charge because of the Roman numeral, but fluorine is -1. So you actually have -6 of them because there's 6 of them. Plus 3 minus 6 is -3. So we're going to need 3 of these potassiums to offset that to make a 0 charge. All right. K3COF6. I mean, you could leave it like that. I'm just going to put brackets around the complex ions because it makes it look cleaner. Like this chunk is the complex ion. Questions on that? All right. So this next page is kind of a sneak peek to organic chemistry. Organic, we're going to really focus on isomers. Oh, what is an isomer? Funny you should ask. All right. So let's get the definition of isomer. It's a compound with the same molecular formula but different structure. So. But different structural formula. Alright, so isomer, compound with the same molecular formula but different structural formula. And this is huge in organic chemistry because the main gist of organic chemistry is carbon and hydrogen being the main components of these molecules. And right here we have, look at this, the same ratio of elements. The difference is how they're structured. So this is the cis conformation, where the electronegative entities are right next to each other. That's higher energy. And then you got the trans conformation, where the electronegative entities are as far away from each other as possible. Same molecular formula, but they have different structure, and therefore different chemicals and, not different chemicals. Sorry. Something went across my background, distracted me. Different chemical properties. All right, structural. Wait, I'm missing something. There's two types. Oh yeah. There's 2 types. Yeah, here it is. There's a structural isomer, and then there's the stereoisomer. So we'll call this type 1. And then we'll call this one type 2. So if we're making a little web diagram, we've got isomer, structural, and stereo. 2 big isomer camps. So a structural isomer is going to be where the isomers contain the same atoms, but 1 or more bonds differ. Alright, so where the isomers contain the same atoms, but 1 or more bonds differ. Here we go, right here, same atoms, but the double bond is between carbon 1 and 2. Right here is between 2 and 3. It's going to have significantly different properties. And we're going to see that in organic chemistry when we get there. That's a structural isomer. So, okay, since we're on the mission of structural isomers, we might as well talk about the 2 kind that pertain to coordination compounds. Well, one's a coordination isomer, and here's an example. It's where the anion is the ligand in one isomer, and it's the anion in the other. So these are coordination isomers. So to get the word definition, it's composition of the complex ion berries. There we go. Composition of the complex ion varies. Really, this is a better definition for my mind, at least. It's like, oh, there's a switcheroo. The anion is the ligand in the other isomer. That's a coordination isomer. Linkage isomer. I believe this is the picture for linkage isomer. No, this is just another. Okay, yeah, here's another picture where here's bromine on the outside, but now it's a ligand. Chlorine's on the outside, now it's a ligand. So another example of coordination isomer. Then we got linkage isomer is where it's even more subtle. It's just where the ligand is linking from a different location. So what's the technical definition? It's composition of the complex ion is the same. The point of attachment of at least one of the ligands is different. I guess let's write the whole thing. Yeah. Composition of the complex ion is the same, but the point of attachment of at least one of the ligands Alright, I really feel for you guys having to do virtual. Oh my gosh, it's probably psychologically damaging. My kids are having a fit. It's only like week 2 for them. And their cousins are over from Colorado and we're supposed to go to a play gallery at 1. They haven't done their homework, so it's like, do we keep them from seeing their cousins that they only see like once or twice a year? Or, you know, let them go to the play gallery without doing their work? So, parent dilemma. What would you guys do? Let's see, there's a chat box. There we go. Make virtual days half days. I'm up for that. Yeah. Although I don't have any voice anymore. Not even on social media. Okay. No way. No, you can't. No, you can't. Oh, like in Michigan? Punish all of them. Oh, our kids, yeah. I was thinking of doing that, so I'm probably going to be soft and give in, and then when we come home, they'll have to finish their homework before bed. So. Yup. Exactly, especially if you're like 4. There we go. Especially if you're 4 or 6. My daughter was crying, and it's like, yeah. Exactly. That's right. Well, maybe Biden can give us a 2 trillion times 2 stimulus and give us universal base income so we can just sit at home and do nothing. That's right. All right. Anyways, getting back to linkage isomerism. Right here we've got NO2 is attaching to the complex ion through the nitrogen. But hey, you have 2 lone pairs of electrons on oxygen. So here's another linkage isomer, and that's going to give slightly different chemical properties. We call those linkage isomers. Right, we got some. All right. So those are structural isomers, and under that umbrella is coordination, and linkage. Alright, then we got stereoisomerism. I think we'll just have enough time to finish that up. So, what is stereoisomerism? The bonds in the isomers, are the same, but the spatial arrangements of the atoms are different. Alright, so that's stereoisomerism. Oh, what does that mean? Okay, so we got a couple of types. We got geometric and optical. Geometric and optical. You're not going to be assessed too much on stereoisomers. Actually, probably not at all in this unit. This is a preview to organic chemistry, which we're going to spend time on. Working with these, they're kind of complicated. So I'm going to have to bring my model set and show you virtually. Hopefully not, because we'll be face-to-face by then. Alright, so we got geometric or cis-trans. Yes, so geometric is that cis-trans. I believe we talked about that. Some, maybe not, unless that was last year I was talking about that. But cis is where you have the electronegativity entities close, and trans, they're far away. So you got field goal, you got walk like an Egyptian, far away. Oh, here's a picture right there. That's convenient. So right here would be trans, and this one would be cis. Field goal, walk like an Egyptian. They're the same conformation, the same bonds. The only difference is, you know, high energy versus low energy, because these don't want to be next to each other, so they have to have more energy in order to be able to be next to each other. Alright, so that's geometric, essentially, in a nutshell. Whereas, oh, here's some more pictures. Look at that. Cis is Latin for on this side, same side, and trans is Latin for across. There's a lot of, you guys probably know about trans nowadays. Alright, optical isomerism. Isomers that have opposite effects on plane polarized light. So this is the really trippy one, kind of hard to wrap your mind around. But my hands are optical isomers because they're mirror images of each other. You can see that? Mirror images. But when I put them on top of each other, my thumb is here and my thumb is there. What? What if this was bromine and that was bromine? These would actually be different molecules with different properties. Kind of like limonene is the chemical responsible for oranges smelling like oranges and lemons smelling like lemons. But the one optical isomer smells like oranges, the other smells like lemons. So specifically different properties. I should have brought my model so that you could see it. But even if you saw it, you have to be able to feel it and see it in your hands to really be able to grasp it. We'll come back to this in the organic unit. But let's just get these quick definitions and then be done. We got chiral and enantiomers. Chiral is objects that have non-superimposable mirror images. And an enantiomer is isomers of non-superimposable mirror images. So enantiomer is the noun, and chiral is the adjective. So what are these isomers? Well, they're chiral, because they have a chiral center. Yeah, they're chiral molecules, so that's an adjective. They are enantiomers, which is a noun. Oh. No, you'd say the enantiomers in this reaction are chiral. There you go, yeah. So an enantiomer is a noun, chiral is an adjective. A little English lesson for you. Adjective describes, nouns represent a person, place, or thing. All right. Oh yeah. So the isomer that rotates plane of light of left is laboratory. So often they're named D, like glucose is dextrose, which is the D optical isomer, or L, laboratory. And it's just showing, it's just a way to represent the different types. That's all we got time for. Sorry I kept a minute too late. Hope you have a great day.